Hi, my name is BD Kim, Byoung Do, or I go by BD. And I'm based in Victoria University of Wellington in Wellington, New Zealand. And today I'm going to talk about my paper, which will be published in the Journal of Number Theory. Its title is slightly different and longer, so I shortened it. Algebraic congruences of Iwasawa theory for non-ordinary primes. So basically what I'll explain is how I'm gonna show the congruences of algebraic p-adic L functions of one modular form and the other modular form, which might have different weights. But what sort of modular forms and what sort of settings am I talking about? So first, let me give a broad picture of things, not just in this paper, but also in this area. Say F2 is an eigenform of a weight 2, and Fk is also an eigenform of weight k, and I want to assume they're congruent, but in what sense? Well, first I'm going to assume that they have the same level, some PM, and the level PM. So here M is some number prime to P. Okay, so what I'm gonna do is I'm gonna assume they're not new forms at P. I assume that they're congruent mod some P to the n, some power of P. And what do I mean by they're congruent? To define the congruence properly, I should say their values at the point on a modular curve of level Pm are congruent mod Pn, but it's probably sufficient to say they're Q expansions for the purpose of this presentation. It's enough to say their P expansions are congruent, and also a natural assumption is their weights are congruent as well. Their weights are congruent as well. So what sort of examples? Well, the primary example that I have in mind is that, okay, and in fact, this is my key example, one that I have in mind. And this is sort of example whose problems that I want to solve eventually. So let's say E is an elliptic curve defined over Q, is defined over Q. And well, then with it, well, there's a new form associated to it. Oh, by the way, let's assume its conductor. Conductor is, let's say M, which is prime to P. And I'm going to assume that it has good supersingular reduction, which is to say good non-ordinary reduction at P, at the prime P. So that A sub P is divisible by P. So in particular, this F sub E is, as we all know, well, it's given by when it's normalized at Q expansion is something like Q plus A to Q square, etc. So that these numbers are where L is a prime not dividing the conductor, A sub L is equal to A sub L of E, which is to say the trace of the Frobenius, well, the L Frobenius on the Tate module of E. And there's a formula for it, which is 1 plus L minus the number of points of E over the finite field of L elements, right? Well, then we can specialize this new form into an old form. So let's say alpha P and beta P are the roots of x squared minus AP plus P, okay? Because we assume E has supersingular reduction at P, neither of them is a p-adic unit. In fact, their p-adic valuation is precisely 1/2. So the p-adic valuation of alpha P and beta P are both 1/2, okay? And okay, I'm gonna let F2, I'm gonna set this equal to Fe minus beta P times Fe Pz, a well-known technique. And then this is an eigenform, well, but not a new form at P, eigenform of level Pm with A sub P of F2 equal to alpha P, right? Now, suppose Fk is also an eigenform, probably not a new form at P, an eigenform of level Pm, and F2 is congruent to Fk mod Pn for some given number, capital N. This is the sort of situation that I'm thinking of. By the way, how do I know? There is such f sub k mod some arbitrary p to the n? I don't know. Well, we do know that there is some eigenform, well, for any weight k, I guess. By the way, yeah, weight k, which is congruent to F2 mod the uniformizer, but not necessarily the power uniformizer by the theory of Coleman-Maser, etc. at all. But mod p to the n, power of p, whether there is such f sub k or not, I don't know. I hope the future research will shed light on it. Anyway, so in such a case, we ideally, well, we hope that there are some p-adic alpha functions. Yeah, let's call it f L sub f2, L sub fk. Well, we hope that there are p-adic alpha functions, L sub f2 associated to f2, L sub fk associated to fk. And well, these padic functions depend on what sort of ZP extension we're talking about, whether it's cyclotomic ZP extension, anti-cyclotomic, or it could be multivariable ZP extension like ZPN, like a ZP, for example, if you have an imaginary quadratic field, then it has okay, let's say this is an imaginary quadratic field. Well, then it has a cyclotomic ZP extension and also anti-cyclotomic ZP extension, but also a bigger extension with Galois group over K is ZP2. So these padic functions depend on what kind of ZP extensions we're talking about. Okay, like in my paper with Seohyun Choi, we had to play with padic functions over this sort of extensions, over this sort of ZP2 extensions. But in the paper that I'm going to discuss today, I will mostly deal with padic. I will mostly deal with cyclotomic ZP extensions. But anyway, so bear in mind that padic functions depend on the ZP extensions that we're talking about. Okay, and depending on the ZP extensions, the existence of padic functions might be known, may not be known. It depends. In any case, okay, suppose we know they exist. We know they exist. Then ideally we think that they are, because F2 and Fk are congruent in principle, we think that their padic functions are congruent as well, except that it may not even make sense to begin with. And that's one of the things that we have to resolve. For example, when P is non-ordinary, these padic functions are not even integral, meaning they're coefficient. Well, so these are power series, basically. Power series of any number of variables. The number of variables depends on what kind of ZP extension we're talking about. If it's ZP2, the two variables. But anyway, so these are power series with the coefficients. If the coefficients are not bounded, if their padic variations are not bounded, then what do I mean by they're congruent? So that's one of the things that we need to resolve to begin with. All right, on the other hand, so this is what I call the analytic picture. On the other hand, the algebraic picture, which is the subject matter of my paper. Algebraic picture is that. All right, so for F2, well, for any eigenform, we know that a Galois representation is attached to it, and Fk as well. It's known by it's not, well, it was, these were constructed by a number of people. And also there's a lattice inside them, invariant under the Galois group. And actually the choice of the lattice is sometimes not such easy matter, but in this paper, the representations will be mostly irreducible, well, actually always irreducible. So the choice will be, choosing these lattices will be canonical, so to speak. So yeah, so it's okay, it's okay. The choice will be canonical pretty much. And then A sub F2, okay, we set A sub F2 be equal to V sub F2, quotient T sub F2, and A sub Fk be V sub Fk, quotient T sub Fk. Okay. Well, then to these discrete representations, discrete Galois representations, we can attach or we can construct Selma groups. And well, and again, in principle, we hope that they're Selma groups because they are because they're congruent. Their representations are congruent in a sense, in a good sense. Then, well, depending on the ZP extension we're talking about, their Selma groups are, well, ideally isomorphic, or at least we think. Although, as it will turn out, what this means is often not so clear when the P is not ordinary, and that's what we will have to deal with as well. Sorry. Well, so this is one way to explain the algebraic congruence, but another way is, which could be slightly less intuitive or possibly slightly more intuitive, but just equally important, is that there's what we may call algebraic p-adic functions. So there's what's called a characteristic ideal of a Selma group. Yeah, literally, it's a characteristic. Yeah, characteristic. And this is an ideal by construction, and it's it's sort of like characteristic of a matrix, so to speak. If you're not familiar with it, okay, so it's an ideal, and in fact, it's a principal ideal by construction. So let's choose its generator. Let's choose a generator, and let's call it L sub Fp, Alg, and also for the characteristic ideal of the Selma group of A sub Fk. Again, by construction, this is a principal ideal, and we can choose a generator, which I'm going to call L sub Fk, Alg. Okay, then we expect they're congruent, just like the analytic p-adic functions. But again, what does it mean? They're congruent. Well, as it turns out, when P is not ordinary, these Selma groups are something horrendous, and the characteristics will be simply 0. So these will be 0, something dumb. 0 doesn't give you any information about any meaningful information. Yeah, so it's hopeless. So instead, we need a better idea. But anyway, so going back to analytic congruences. So what have I done in this regard? Okay, going back to the analytic congruence. So this congruence, the congruence of analytic p-adic functions. which, by the way, interpolate what we call the interpolate the special values of L functions, complex L functions twisted by characters. What I did with Seohyun Choi which was published in 2017 and Ramanujan journal, is that in fact their p-adic L functions. Okay, I'm gonna write it. I'm gonna write it by this fancy L f sub k minus fancy L f sub 2, and I'm using a different non-standard notation because these are two variable p-adic L functions, not like one variable cyclotomic p-adic L functions over cyclotomic ZP extension, but rather two variable F functions with respect to this ZP2 extension of an imaginary quadratic field. Why did we use these p-adic L functions? Because mainly because that was what I constructed. Yeah, that was what I constructed, and also because turns out it turns out our ideas were particularly relevant for these to these p-adic L functions. But anyway, so these are for good reason. These are not integral, meaning their coefficients are divergent in p-adic sense. So precisely, they're in some set of power series. Let's call it P. So this P is the set of power series. Yeah, power series of two variables. Let's say two variables. So that at there's a precise formula or restriction for the coefficients. So the p-adic norm of its coefficients is bounded by a sub p of f2 raised by I plus j. Well, actually, there's one here as well. So what are ij? Well, yeah, I is any number, so that m is smaller than p to the I, and j is any number, so that n is smaller than p to the j. Okay. So it looks like p is something rather complicated. So note that these are divergent, but there's a precise restriction for its growth. So we can say, we can call it its growth rate. But actually, if you know, for instance, Penrose paper, this will look, if you know Penrose paper, this will look rather natural. This is a special kind of admissibility. So anyway, so LFK minus LF2 is contained in P to the N, P to the NP. Okay, P to the NP. So that was the kind of congruence that we obtained. Okay, then what about my new paper? So my new paper that will be published in the Journal of Number Theory. I do the algebraic counterpart of this result, in a sense. So in the new paper, what I do is the algebraic, counterpart. Okay, just a second. Yeah, let me check if this is getting recorded. All right. And well, to do that, it takes some work. Oh, by the way, important thing. So in this paper, we had to assume a lot of Gorenstein hypothesis. So what do I mean by that is that we had to assume that a number of localized, a number of Hecke algebras localized by the maximal ideals associated to F2 or Fk are Gorenstein, and this sort of excuse me, and this sort of assumptions or this sort of questions are fairly common, fairly common in many areas, and often, in a lot of cases, they're actually solved. Like for instance, in the famous and Andrew Wiles's famous proof of Fermat's last theorem, he had to prove a number of Gorenstein hypotheses. Or sometimes he didn't have to, but it he just proved it as as on a side note. The Gorenstein hypothesis followed as a result of his proof sometimes. But anyway, but we had to assume a much larger class of Gorenstein hypothesis. Like we had to assume the Gorensteinness for a larger class of Hecke algebras. Especially the problem was the higher weight, when weight is not 2, like in Wiles's paper, he dealt with Hecke algebras of weight 2, but for higher weights, much less is known. So we had to assume a lot of Gorenstein hypotheses, and well, we hope that they will be resolved in the future. Okay, now back to algebraic counterpart. We don't have to assume any Gorenstein hypothesis, thankfully. Anyway, so what we did, first we had to construct, I had to construct p-adic L functions. P-adic L functions like this, the generators of the characteristic ideals of the sum of groups, or rather the Pontryagin duals of the sum of groups. And this construction doesn't actually involve the sum of groups, which is hopeless because the sum of groups for non-ordinary primes are horrendous. So construction through sum of groups is just hopeless. Instead, how do we do it? Well, how do I do it? By way of Perrin-Riaux. And I don't have time to explain that. But anyway, so the inspiration is Perrin-Riaux's paper. So what she did, well, she constructed these nice local points. We can call them like plus minus points, except that they're not. Unless like in a nice case, like weight is 2, a sub p is 0. Yeah, they're not plus minus points, but anyway. And using those points, and how did she construct them? Well, sometimes, well, like in the elliptic curve case, she used Fontaine's, Fontaine's theory of formal group schemes, which is about like this nice functor using COVID vectors and so on. And for higher weight case, like more generally, for more general Galois representations, she used what they used to call B crystals, or p-adic Hodge theory, very cleverly. And I had to use her ideas a lot, but that's not all. So what do? Well, you have to construct some local points, or actually for higher weights, they're not really points. So I don't know, you can call them cohomological cycles. And then you need to show the congruences. Congruences between the points for F2 and the cohomological cycles for Fk. You need to show their congruences, and this is pretty hard. This is pretty hard because their weights are different, and that means implies a lot of things. It makes comparing them directly impossible. So you need to come up with a different idea. But anyway, so that was done. So I did that. So I did that precisely. And then as a result, well, plus some other ideas, what I did was that okay, for any character, chi of, let's say, a gal Qn Q. So this is the subfield of the cyclotomic ZP extensions. You know, like the subfield of Q joined by p to the n plus 1th root of unities, roots of unity. Yeah, for any such character, I show that the p-adic valuation of chi of L F2 Lg is equal to the p-adic valuation of chi L F sub k Lg. And it may not look like it, but it is actually a congruence statement. In fact, I'm pretty sure that I can restate my result in terms of a proper congruence, like so probably I can also show with more work, I can also show something like L sub F2 Lg minus L sub Fk Lg as inside the difference is p to the n times the certain set of power series p, like in my paper with Sion Choi, but I didn't really bother with that. Anyway, so this is the result I got, and using this plus some other ideas involving showing precise relation between L sub F2 Lg and plus minus p-adic functions of Kobayashi, and et cetera, I could also show that, plus my previous paper with Choi, I could also show that the main conjecture of Iwasawa theory for F sub k, if that can be proven, then that implies the main conjecture of Iwasawa theory for F2 But yeah, but I didn't make too big of a deal about it. I didn't make a too big of a deal about it because that was not at all my main focus. My main focus is this algebraic congruence, and I think that is, in my opinion, that is interesting in and of its own, in and of itself. So I'll stop here. Thank you.